Now Joshua Mora from AMD will be presenting on Bulldozer.
Thanks, Brian. Well, good afternoon to everyone. We got 30 minutes to have some talk about the Bulldozer Architecture, which is one of the key components of the new processor named Interlagos. I hope that this presentation is very, very pragmatic for most of you. I hope you can really go back into your labs, and if you're having Interlagos processors, then you can apply the things that I'm going to be going over in here. That's, from my point of view, what it is the HPC Advisory Council to give best practices. Okay. Right, so this is the agenda. I'm going to go over a little bit, let me see the pointer. Okay. So I'm going to go about a little bit infrastructure, and then fairly soon I'm going to get into one of the key components of the Bulldozer, which is a floating point instruction. I think it's important that I spend a lot of time in there so people can understand really what's the value of that architecture. And then I'll be providing some performance data that you can go and replicate in your labs. You have my email over there, so if you run into issues with that, I'll be more than happy to help you, okay? So let's go in there. I don't know if you are familiar with it. I'm going to try to do a summary on it. So this is how it looks, processor. It's the socket G34. And in here you have 8 cores plus 8 cores, a total of 16 cores. And I just put here some numbers, like a 2.3 gigahertz core with 4 Bulldozer units. Here it's 1, 2, 3, and 4. And another 4 Bulldozer units in here. Each of those have L2s, L1s inside, and then here you got an L3 being shared among all of those. And then they are connected through coherent hypertransport, and then this model in here has 2 memory channels, and then this has 2 memory channels, so the total is 4 memory channels. And this whole thing is capable of delivering real numbers, not theoretical, about 18.5 gigabytes per second times 2. And this model is capable of 60 double precision gigaflops, so times 2 for the whole thing. And everything is under 130 watts. And I put in here in parentheses 115 watts. That's the number that AMD would give you. But this is the number that you would get at most when you're running actually LINPACK. When you're running regular applications, it will only get 115 watts. But when you're running LINPACK, it's going to consume up to 130 watts. And I'll explain also why you get 130 rather than 115. Okay, so this is the Bulldozer unit, or the compute unit that I was showing here. Here it is. And what I wanted to point out here, this is kind of a sort of a marketing slide where they show you, okay, these are individual resources, and then here you got a L2, which is share, and then these are also shared resources. And then this is the part where I'm going to be focusing or conversation, okay? And I'll be going through some exercises that you can replicate, as I said. And so the idea on this design is that you could have under this compute unit having a thread or a process that runs through this one resource, and then the other can go through this other resource and has integer compute units, and then has integer compute unit this one, but then there is this floating point unit in here that is shared. So either one can use a portion of it, or it can use it all. So you have a lot of flexibility, okay? And we'll be exploring that flexibility through some examples. So for example, you can imagine, I mean, under HPC, everything like OpenMP applications or MPI, everything runs at the same time, number crunching. It could be floating point or it could be integer. So then if it's integer, then you got your own resources independently for each of those cores. But then this is the floating point unit, which is shared, so kind of one of the cores uses some amount of those resources, and then the other uses that. But you could have only integer-based workload, and then the other could use the whole floating point unit. So that's the kind of flexibility we are looking for. Okay? I wanted to put this, I didn't have this slide at the beginning, but I ended up putting it because it may later on help people understand better things. For example, let me just kind of explain here that you're bringing data from the main memory, which could be down here, to the L2, which was a shared resource. And then you're bringing it to each of the L1s, which are, like here, you see they are independent, right? L1. So the L2 is bringing data to the L2s. And then from there, well, this is especially for the floating point unit, because I'm going to be focusing there. Then you bring the instructions in here, the kind of computation you're going to, the operations you want to do on what data, and then you bring that to floating point, load buffer, and then you're going to be executing floating point operations, and then returning the result back into the data cache, and then back into the L2 through this thing. It's called write combined cacher. Okay. And if I look a little bit into the floating point unit, I want to mention that once you get the data of the operations, then you can have a bunch of those operations scheduled, and then you send those to the different floating point pipes, which have different type of floating point operations that are kind of listed in here. And I'm going to be focusing on this talk on the FMAC. Okay, you can, for example, I'll be showing some examples using SSE2 type of operations and also FMA4 type of operations. Okay, and I want you to realize that all of these things, these kind of 4 pipes with these different type of operations are all in here. And this, bless you, and this is the floating point unit. So they're going to be coming here instructions. It doesn't matter really whether they are coming from this core or this other core. I mean, if it's coming from this one, then the result is going to go back into this one or in the other one. That's why I was showing here this. So they're coming from this core, then coming this way and then send back. They're coming from this other one, coming here and send back, okay? All right, and these are on the pipe 0, these are the type of operations that are being executed. And on the pipe 1, also same kind. So these 2 can issue the same type of operations. And then these are other operations for the pipe 2 and pipe 3. And we're going to be focusing on these 2 pipes out of the 4 pipes. So in here, let me see. Here we are just showing actually 2 of those 4 pipes, the FMAC, okay? But there are 4, pipe 0, 1, 2, and 3. So we're going to be just looking into these 2 in here, okay? All right. So here it's let me see. So these instructions that I was showing here, I just put in here, if you look at, there's a document called Software Optimization Guide for the Interlagos or Family 15. And you can look at different type of instructions and it tells you how long it takes that instruction to be executed, okay? I don't want to scare you with these kind of low-level details, but I just want you to understand a little bit better how things go, okay? And these are, FMA stands for fuse, multiply, add. I'm going to explain a little bit how that works. And then this V stands for the vector, okay? And then here it tells you that document for that kind of instruction on what pipe is being executed. So it's telling you that these FMA instructions are being executed on the pipe 0 and pipe 1, okay? There'll be other instructions that will tell you, okay, then those are, for instance, executed on pipe 1 and pipe 3, all right? Okay, so those 2 pipes that I was telling you, okay, FMA, fuse, multiply, add, accumulate 1 pipeline, and then these are 1, okay? So here's where, through the scheduler, which is kind of it's called round robin, then you're feeding to this pipe and this other pipe at the same time with instructions. And it could be instructions that are doing like this multiplication or this addition in such a way that when you're adding the numbers, then the result gets into one container, which is the same one as you had. For example, I'm using all the time here A. So A times B, you put the result into A. Or here, C times D, you put the result into C. And on addition, it's A plus C, and the result into A, and so on, for example. Okay. So this is also like a container of 128 bit. So this is a pipeline of 128 bit, and then another one. And when you're doing these results, you're actually having operations that are 64-bit operations, but because this is a container of 128-bit, then it gets executed this kind of operation 2 at a time, needing only 6 clocks. And those 6 clocks is the number that I was looking here, okay? And then when you get started at one of those operations, then at the next clock, you can put another one and so on. I'm just painting 2 in here, but then you can pipeline many of those, okay? And then at the same time, on this other pipe does the same thing. And for example, I'm putting in here like the kind of operations I'm trying to put. The parentheses is kind of defining some order of the operations. Like I want to do A times B and then add C times D. So, okay, A times B, I have it here, and then C times D, I have it here. But once they are both completed, then I can start the A plus C, but the C was this value. So then this part in here would be this. Kind of drawing some examples. And this is what's going on the first pipeline, and this is what's going on the second pipeline. But if you look at any given clock, you're retiring this bucket of instructions or this bucket, and you see this addition, but this addition is being done on this, but because it's a 128-bit, there are 2 of those being computed at the same time. So there are 2 of double precision additions being done here, or down here, for example, I'm putting 2 double precision multiplications at every clock. And this is what's happening on this pipeline, and at the same time, it's happening the same on this other pipeline. So at any given clock, if I use SSE2 type of operations, I get a total of, like, for example, these 2 plus these 2, 4 double precision, or these 2 plus these 2, 4 double precision operations, always. And I didn't mention whether this was just done by 2 processes or 1 process. The process or 2 processes, they are putting here instructions to be executed, and then you're just filling up these pipelines, and they get executed and retired, and then sent out back to the corresponding data cache. If I move to FMA for instructions, then those FMA for instructions are allowing you to do, in those 6 clocks, not only an addition, but also multiplication. So you're really multiplying by a factor of 2 the capability per clock of executing floating point operations using those 2 FMAC pipelines. So basically, this Bulldozer unit is capable per clock of issuing up to 8 double precision, or it would be also 16 single precision floating point operations per clock at the whole Bulldozer unit, okay? Okay, so for example, imagine I had only 1 thread and I'm using both pipelines, so they are really fast. You can try to fill them up, but this is not fast enough to fill up the whole, both 2 pipelines. So the overall efficiency of this, it won't put all, per clock, you will not be able to retire always 8. You may be able to retire up to 7 or something like that. So that's kind of something like an 85% of efficiency of utilization, because they can consume a lot. With when I put those 2 threads, you're almost filling it up completely, so then you get like 95% of efficiency, okay? All right, so that's the kind of the fundamentals. Then I'm going to go into some benchmarking, and here are the software ecosystem that I'm using. You have to use an operating system that supports Interlagos. Here I list them all. Don't go with something earlier than this, because then you will not exploit properly the architecture. You have to use a compiler that is actually capable of generating this kind of instructions. Otherwise, if you use these other instructions, you only will be able to use and issue a total no more than 4 double precision flops per clock. You have to use a compiler that is capable of issuing these FMA instructions in order to enjoy and exploit those 8 double precision per clock. Okay, very important. All right. Okay. Then you can definitely exploit math libraries that have Interlagos, or Bulldozer support those FMA instructions. You don't have to write those FMA instructions by yourself. You can use the AMD Core Math library, which is available, download. And also there is the LibM that usually comes with the operating system. You can use this one from AMD as well, and you will be able to exploit those instructions. And then if you want to know what's going on in terms of profiling, then you can use Code Analyst or the OProfile or PAPI or Perf. All of those are open source. You can get them. And I provide more information at the end. Okay, I don't know if you're familiar with FMA instructions, but for example, if you look at the DGEM benchmark, which is not benchmark like this kernel operation, which is the product of two matrices, and I do a very simple example in here. Like I multiply this row by this column, and I put the result in here. You see that this is a product plus an addition plus product, blah, blah, blah. So if I make like a generic statement in here, A times B, so this inner product, you know, it's plenty of those multiplies and adds that I can express as FMA4, okay? So we are going to be basically showing you what's the difference between using SSE2 instructions and FMA4 instructions in a matrix multiplication, okay? So if I use the SSE instructions, then I will be able to use out of the potential of 8 flops, 8 double precision flops, only 4. So I'll be only hitting about 50% of efficiency, no matter whether I use only one thread or 2 threads. With one thread, as I was mentioning before, you had about 85% of efficiency because you could not fill up both pipelines well. But then when you put the second one, then you're maximizing the usage of both pipelines. So that kind of 45% is about that 85% number that we were talking with respect to the utilization of both pipelines. I mean, the maximum you would be able to get is about 50% efficiency when using SSE. When I go into FMAs, then it bumps to like 85% of efficiency with only one thread. And then if I use the second thread, it goes about something like 94, okay? And these were some tests that I did using, for instance, OpenMP. And then you increase the problem size and then kind of trying to fill out those pipelines and try to get as much usage as possible of those 2 pipelines, okay? Then I did a test because the Bulldozer unit, it's replicated, you know, on a NUMA node up to 4, so you got a total of 8 threads, and then you would have the socket 16. So I'm just running the same example, but using more threads. And I just want to point out that when you're running tiny problems, then there is a OpenMP overhead, you know, that it's going to prevent you to have good efficiencies. And if you run larger problems, then you can hit higher efficiencies. This is an 8-thread run using 4 Bulldozer units. And then when you're using less threads, then you get higher numbers. So this is actually telling you that, for example, if you're running LINPACK, don't run it with multi-threading because LINPACK is going to be running at problem sizes. Well, one thing is the n problem size, another is when you're breaking that, you know, into the NB parameter. So that's numbered down here. So you want to run not even multi-threaded 2 threads here because the efficiency would be low. You actually want to be using single threaded, which is going to be here at 80-something% efficiency. Yeah, go ahead. That's a very good question, and I don't have the answer. I haven't tried several compilers to see that runtime overhead. This was done with the Open64 compiler. Okay, that's a very good question. In general, when I'm running LINPACK, I don't run it with multi-threaded because I see always like 1, 2, or 3% lower performance when I run multi-threaded. Okay, I must say that, for example, before Katsushige Goto was doing LINPACK runs and so on, well, the DGEM, he was using pthreads, which has lower overhead. Here we're talking using OpenMP, so it seems to have higher overhead than pthreads. We at the AMD Core Math Library, ACML, does not use pthreads as an implementation. It uses OpenMP. Okay, but definitely I told the guys at ACML that they may want to investigate how to reduce this runtime overhead on the OpenMP. Okay, that's a good question. Okay, so talking about the DGEM, you know, in terms of efficiency of the floating point architecture, it translates very well into what it's going to look like then the efficiency on the LINPACK. Okay, so for example, if you do the profiling of the application, then you'll see that most of the percentage time of LINPACK is spent on the DGEM, and about 7% of the time is spent on communications, either through the shared memory for internal communications or internal communications on InfiniBand. And also talking about DGEM efficiency would be the same as talking about HPL efficiency. talking about the DGEM power consumption would be the same as talking about the LINPACK power consumption. Okay? And then let's look into some results on the LINPACK and so on, using ACML with FMA4, okay? So we can exploit those 8 flops on the Bulldozer unit. Because the Bulldozer module or unit has 2 cores, you could say that every core can issue 4 flops, but you can have only 1 core out of the Bulldozer unit, and it will be able to use up to that 85% of the 2 F max. So you can actually get about 7 flops per clock on that single core that you're using. But if you really want to use as much as possible of that Bulldozer unit, then you're forced to use the second core as well, even if you're just going to get an extra 10% at most. But you're going to get closer to the overall efficiency. Okay? So I don't know if you're familiar with the code analyst, but it's, as I said, it's a tool that you can download. It's free to use and so on. And basically, I was running LINPACK, and then, well, basically the time is spent at the ASML library, some amount of time is spent on the Intel MPI, at the OpenMPI, yeah, Open64, yeah. OpenMPI built with Open64. And then some other time spent on the additional calls on the LINPACK benchmark. Here you can see some other shared memory communications going on the MPI. Okay. By the way, I also look at the kind of floating point operations that are being executed or retired. And you can see that most of them spent on the ACML were of type FMA4. It doesn't put that FMA4. I put that myself. It's just that when you put the type of operations, then I knew that the first column was going to be FMAs, and the second column was going to be SSA2. But basically, I wanted to double check that there were no SSA2 instructions being retired. And that's because I'm using the ACML FMA4, okay? Then if I double click on the ACML, okay, and I want to see where it's spending the time, then what's happening is that about 82% of the time was being spent on the double precision matrix kernel for Bulldozer, which is what makes sense for LINPACK, being spent most of the time on the DGEM kernel, okay? And again, I look at the nature of operations, and it's FMA4s, all right? And no time is spent on SSE2s, there are none. So be careful if you're using on an Interlagos system ACML using SSE2, because then out of the 8 double precision flops that you can exploit, you will be only getting 4. So you'll get something like 45, 50% of efficiency on your system if you don't use the FMA4 version. All right. I don't know how. Okay, 7 minutes more. Okay, I want to comment also on the power management. That's another feature on the processor. Here, there is a bunch of applications that are considered like compute intensive. And then this is what AMD goes out there saying, okay, this processor cannot consume more than 115 watt. But the majority of the applications stay way below that. So this is basically room for boosting the core frequencies as long as we don't pass that power consumption. Now, LINPACK is just an exception that at the regular frequencies, say at 2.3 gigahertz, and these are lower frequencies, it's already consuming way over that TDP number, okay, way over. So if we apply the boost, it works on both directions. I mean, for those workloads, since you are below the TDP, it's going to speed them up, it's going to overclock the frequencies. But on this one, it's going to say you're burning too much power, so I'm going to lower actually the core frequency. And if you lower the core frequency, then it's going to drop your LINPACK score. So one thing you can do is just disable then the boost capability, so it's going to consume more power, so what? We want to keep a good performance number, okay? And so these are the boost states that for LINPACK would not make actually sense, but for these other applications, definitely it can boost. So, for example, here is the regular frequencies of the operating system. These are frequency when you're running nothing, it's at idle, and these are the boost frequencies. So one way to do things is without disabling the advanced power management, because LINPACK is just for an acceptance test, right? But later on when you run your real applications, you really want to enjoy the boost. But you want to go and disable the APM thing, and then once you're done with the LINPACK, then you want to enable it again for your applications to take profit, or simply you can do this thing that we call HPC mode, so you don't have to touch the BIOS. You keep it enabled, APM. And what we are doing is, these frequencies in the middle, we set them all at 2.3 gigahertz for this processor, and then you keep those for boost, and this for power savings. So what happens is when your application is, when you're running LINPACK on your system, you're running at the base frequency of 2.3, it's saying, okay, I'm getting too hot, so I'm going to lower the frequency, fine. I'm going to go into the lower power state, so it's going into P1, but guess what? We cheated to the processor, right? And we keep it at 2.3. Oh, it's still too hot, okay, I'm going to go down. And it's going to stay hovering in here, but it's going to stay always at 2.3. So it doesn't impact on your LINPACK score, okay? But for any other applications, you're going to be at 2.3, and then it says, oh, you're not consuming all the power, right, because you're below here, so I'm going to do a boost, and that's fine. You can enjoy that boost. When you're not running anything, it's going to go down. So then the HPC mode is not going to be hurting your applications, you know. It's going to leverage the boost capability. So you can apply then this HPC mode, and this is either available, this feature, through the BIOS of the vendor, or also there is a tool that you can also download from here, and you can basically set up this behavior, okay? And finally, here are some results. Imagine that I'm running with a boost enabled, but this HPC mode is disabled. So it's not going to be, it's going to throttle down the frequency because it's burning too much power. So you're not going to get good efficiencies. And if I, for example, enable this, then I can increase the efficiencies because it's going to stay all the time at the right base frequency. So for LINPACK, definitely you want to use this HPC mode enabled, all right? And then you will be able to get the right performance. Now, another interesting thing is that at the power consumption of the system, because I have this feature enabled, then I'm preventing the applications to go above the TDP number. So then it's consuming 115 watt each processor. But if I apply this, definitely I'm going to allow it to stay always at the same frequency, so it's going to burn more power, okay? So it's, here is what I'm putting, the 475 watt for that processor, okay? Now this would only be for the LINPACK application. For any other application, you're going to be always below here, and it's going to be able to go up to the TDP number, okay? Okay. And finally, and it's a shame that the guys of Intel left. I don't know if there's anyone here from Intel. No? Because I asked them a question about their cluster ready. So here is the answer to the question that they didn't have. Basically, I asked them if under the cluster ready, they could have a way to detect thermal problems, right? And they say, well, we don't have this. Of course, it can be implemented and so on. Okay, so this is a way that you can test on your cluster whether you're running into thermal problems or not. Basically, you were asking, I'm not going to point you with the laser, but you were asking about the BIOS, how to read things. So both AMD and Intel, there is the PCI register. You can read values, and then you can look at those, and a lot of the BIOS settings are hard-coded into these PCI registers that you can read. You need to know them. So you have to use the right document that tells you for the PCI register what you need to look at. For example, on the AMD side, if a processor was getting too hot, then it flips a bit up that you can read on the PCI. So for example, imagine that this is a system with 4 processors. So you have to go into this and read this .3 in here. It gives you a chunk of numbers. And then you go in there, and then there's a special, on an offset of 60, there is a value that it's either a 1 or a 0. And it will tell me, for example, if it is a 1, that it's doing thermal throttling, and if it is a 0, then it will tell me that that processor is fine. Okay? Like, for example, if you want to know on QDR InfiniBand if it's at certain transfer rate, you can go into the, correct me if I'm wrong, but you can go, Todd is here, Ron? Maybe Todd? Okay, well, anyway, you can go into the PCI and look at the registers, and you'll see the bandwidth, for example, if it's, or if it's, you know, if you can look at all the BIOS settings to PCI registers, okay? And then you can, then what I'm doing is, this is just a script that you can run then on the whole cluster. And then I just look for the TT number, for example, and it will tell me that, okay, the second processor, for example, on a given compute node is running to thermal throttling, so you can go and then get that fixed, And it's important that you get those problems fixed, because if it's doing thermal throttling, then it's too hot, right? Then it's going to throttle down the frequencies, and it's going to impact on the performance of your LINPACK. Okay? So I think that's all. And then for building this presentation, I use material that you can download, like the Open64 compiler or code analyst, HTML. This is where you go into the developer.amd and kind of this tool section on the compiler on, I recommend you to look into the software optimization guide and compiler options. There's a Linux tuning guide as well. I recommend you to go in there. And then for the LINPACK and tools in there, you can get those from there. And if you have questions, then we have a developer forum you can ask. And you got my email as well. So anyone that is running LINPACK, for example, and not reaching the right performance, you should try to look into this or send me an email, and I'll be more than happy to help you. So I'm done. If you guys have questions, I'll be more than happy to answer them now or later on during the ISE conference. Yeah?
Do you happen to know when your FMA4 instruction will be included by the Intel compiler for AMD CPUs? And second question, what is the status of these FMA4 optimizations for ISV codes, for the IT codes for HPC?
Okay, all right. The first question you must agree that I can't answer, because that's a question for Intel guys, right? But let me explain you what I think. We are having FMA4 instructions. And if you go into Wikipedia and look for the history of FMA4 instructions, or FMA also in general, there are FMA4 and FMA3, all right? So AMD proposed to go with FMA3 instructions, and Intel wanted to go with FMA4. And when we started actually then saying, okay, well, then Intel will have FMA3 instructions in there, because they want to go with, FMA4 instructions. And so we will build our processor with FMA4 instructions. And then at some point, Intel changed their mind. They said, we're going to do actually FMA3 instructions. So their compiler will issue FMA3 instructions. That basically means that Intel compiler cannot issue FMA4 instructions. So you cannot use Intel compiler to get those 8 precision floats per clock. Now, the next generation processor that we're shipping fairly soon, named Abu Dhabi, that will have not only the FMA4s, but also the FMA3. That basically means that when Intel is shipping their processor, at some point that will have FMA3 instructions, their compiler, that will be issuing FMA3 instructions, we will be able to also leverage that compiler on our processor, not on the Interlagos, but on the Abu Dhabi. So you can use GCC compiler or PGI or Open64, yes, all those three, to get FMA4 and FMA3 instructions. FMA3, you can't use them on Interlagos. You will be able to use them on the Abu Dhabi. But you have to know the difference between FMA3 and FMA4. FMA4 has more flexibility, actually, because you got A times B plus C, and then the result into D, for example, right? So actually, I tested it already on the Abu Dhabi. There is no advantage of FMA3 with respect to FMA4. There isn't. But what it's true is that Intel compiler is really good. So whenever they're going to be issuing FMA3s, then on the Abu Dhabi we will be able to exploit them. But until then, you have to use a compiler that issues FMA4. Okay. And then the second question was ISV codes. Well, so I guess the answer is related with this as well. If you want an application to exploit Interlagos architecture and FMA4 instructions, then you would have to twist their arm, and tell them to use Open64 compiler or GCC or PGI compiler, right? You have to give them arguments like the ones that I provided in here to tell them if you don't use the right instructions, then you are limiting your performance by half. One thing I should say, though, is that LINPACK or the DGEM, it's a special case, because on LINPACK you're spending about 85% of the time or 90% of the time only doing that kind of operations, FMA. So it's a great marketing example, so to speak, to say you got to use those instructions if you really want double the performance, right? Real applications, they spend maybe 5% or 10% of their time potentially using that kind of instructions, right? So then the benefit is in that 5 to 10%, then you can boost by twice. But that doesn't mean that the overall application, if you're not using FMA4, for example, you're going to get twice the performance, right? Does it answer the question? All right. Yeah, go ahead.
Your measurements for DGEM.
Yes.
The dimensions start at 200 and then it increased slowly until you had the maximum performance.
Mm-hmm.
How can you get better performance for smaller dimensions, say up to 1,000 or so?
Single-threaded. You keep single thread, you see it stays pretty flat.
You can't go beyond 90% then.
What?
You can't go beyond.
Oh, if you remember, if I use, okay. First of all, here what I'm trying to demonstrate is that with only one thread, I can use both pipelines and achieve about 85%, okay? But you don't have to get crazy on that. You can use simply 2 threads running sequentially, and you're scheduling floating point units to both pipelines. You'll get to use them both better than if you just did one. What I'm trying to say is that for instance, when I'm running LINPACK Benchmark, every MPI process doesn't spawn multi-threading, and you're having 2 MPI processes scheduling instructions to both pipes. So the overall utilization of them is 95%. What I was trying to show in here is that if I only use, out of the total Bulldozer unit with those 2 pipes, only 1 thread, you're not using it all because this is really fat and this is not fast enough to fit them all. But with this here, it's those 2 pipes, and I'm using 2 threads, not an OpenMP necessarily, but one MPI process and another MPI process. Don't get me wrong when I said this, it's because you put 2 MPI processes here and then they're sending FPU instructions to both. You're filling them up better. Okay? Sure. What? A compare? I don't know. If you send me an email I'll check on that. I don't know. I don't know. Wait a second. So if you got 2 threads, no, sorry, the compare is between 2 threads? Yes. Well, in here and these 2 pipes, at this point in here, you're not separating information. You don't have here data and then here for 2 different threads. Those 2 threads are sending instructions in here, and then they will get sent out either into this pipe or this other. Yeah. 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 To be honest with you, I don't know. Send me an email with the exact case, and I will look into it. I will look into it. Okay? Yeah. I'll be more than happy to. And if you have even a case that you see on a regular application, for example, that would be great to look into. Okay? Any other questions? All right. Thanks. Oh, yeah, go ahead.
You mentioned about the thermal problem. So what's better, to use a single core and boost up frequency, or to use double cores with lower?
Okay. All right. That's also a very good question. Certainly, I didn't want to spend time in here going through that, but what happens is, okay, let's go in here into the, I think I'm passing already quite a bit of time, right? Okay, so what happens is, if you're using only 1 thread, okay, it's going to burn a certain amount of power. If you use the 2nd thread, it's not going to add additional power because they are both threads into the same Bulldozer unit. So the extra boost that you can get by not using the 2nd thread, it's very, very minimal. Another thing would be that you stop using Bulldozer units, then all that energy gets into the other remaining Bulldozer units that you're using, and then there you really get boost. But if you're having a run done with 2 threads on the same Bulldozer unit and you just remove 1, you will not get a substantial increase on the core frequencies. In order to get a substantial increase, you have to stop using some, which is very interesting for single-threaded licensed applications. Why? Because here you can see that you can go to a boost of, say, this is the base frequency. You buy a processor, say, at 2.3 gigahertz, but it can sustain up to 3.2 gigahertz for an application if you're not using more than just the first Bulldozer unit on an application that is not parallel. So then you're going to be able to run that at 3.2 gigahertz. That's a kind of a way of exploiting the boost. Okay. Yeah, I'm sorry that I went over 10 minutes, I think.